to spend a little more time on them. Okay, thanks to Matthew, we screwed up my whole plans.
Sorry.
All right, encryption and decryption. Okay, the way this works is we have some plain text, we have some ciphertext, plus we also have a sender and receiver and how we're going to get it there. Okay, we could have interruption along the way, we could have interception, modification, fabrication. I mentioned a little bit of that stuff earlier. All this stuff could happen to our messages. Okay, this is the very, very, very basics. Okay, cryptography is using encryption to conceal plain text. Okay, cryptanalysis is trying to figure out that jumbled up text. It's basically the code breaking aspect of it, and cryptology is actually put together. Did I say that wrong? Okay, yeah, but that's what it is. I might have said the wrong word there. Okay. Breakable encryption is the analysts can determine the algorithm given enough time and data. So if I give you unlimited amount of time and unlimited amount of plain text data and encrypted data, you think you can figure out how it was done? Probably. Probably. Okay. Theoretically breakable says practically unbreakable. Okay. But, you know, it's kind of like if you've never seen this website, I'm going to show you real quick. Okay. If you haven't used it, you need to. It's called How Secure Is My Password.com, I think. Or is it .net? Damn it, it's .net. Okay. I'm going to go in there and I'm going to type in my current LastPass password. There it is. That is my password to log into my password vault. Will take a quintillion years to break. How is that? How do they know that? No one's been alive for a quintillion years. But what they're saying is based on current technology, theoretically it would be broken in that length of time. Okay? If you've never been to this website, you need to go there. It's kind of cool. Okay? All right, brute force attacks, we're going to try everything. It's, ATM machines. What are those made up of? 4 numbers? Come on, the odds are you can get those pretty easily. I mean, there's not that many possible choices.
He said the most common pin is 1113.
1113?
Yeah.
That's weird. Okay.
I don't know. I don't know why.
Yeah, that's weird.
About 2 months ago.
Huh. But brute force attacks is try every combination. I do talk more about that in another lecture. Ingenious attacks, we'll talk more about that in a minute, but maybe someone just thinks this, hey, what about this? And it works. Okay? All right, estimates of breakability based on current technology. There's that Moore's law I was telling you about. It says number of transistors on a chip double every 2 years. Basically, the speed of your computer doubles. It's actually 18 months. But okay. If you haven't seen this movie, Mercury Rising, it's kind of cool. Some government agency puts out this puzzle book, and this kid solves it. And they're like, whoa, no one's ever been able to solve that puzzle, and they start going crazy. Kind of an interesting movie. How about Rain Man? There's people like that out there. Okay. My stepson has autism, Asperger's, one of them A things. But he real good at math. I taught him binary in like 5 minutes. And he went to school. He tried to explain it to the bus driver. Didn't go over so well. He was trying to explain it to all his classmates. They had no clue. He went to his math teacher. Math teacher had no clue. But he was coming home. He'd write messages on the board in binary and everything else. I'm like, wow. But, he's good with math. Now, not good with much else, but he's good with math. But, there's people out there. So just because it's unbreakable doesn't mean there's not someone like this. Okay. All right. Basic encryption. We have a key-based cipher. It says provides more security than a keyless. Okay. You encrypt with a key, then decrypt with a key. Easy enough. You lock it with a key, you unlock it with a key. Okay. So we take our plain text right here, and we use our encryption key to encrypt our plain text. We get our ciphertext. Easy enough? That's the third bullet. So basically, if I took my plain text over here and encrypted it with a key, and took that result and decrypted it with a key, would that not be the plain text again? I encrypted it, then decrypted it. Same way here, I took my ciphertext, decrypted, it become plain text. So these all are equal. Okay? That's about as hard as the math gets. It's not that difficult. Okay? Symmetric means same key. I use the same key to encrypt and decrypt. Asymmetric is a different key. I encrypt with one, I decrypt with a different. Okay? Easiest way to remember them, symmetric, same key. S. Symmetric, same key. That will be on both tests. Now I said some stuff will be, yeah, that's on both tests. So symmetric, same key. Asymmetric, different key. All right, symmetric encryption is an encryption algorithm where the same key is used for both encryption and decryption. The key must be kept secret. So if I lose the key to encrypt it, what happens to the key that I used to decrypt it?
Lost it.
It's the same key. It's out there, okay? So the key must be kept secret. It's shared by the message sender and recipient. So if I want to encrypt something and share it with Austin, he needs to have the same key. I still have an issue getting him the key. We haven't talked about that yet. We'll get to there. But okay? So with symmetric or secret key, it's also known as, and also private key. It's all the same name. Symmetric, secret, private, they're all the same name. Okay? So encryption, decryption are the same. There's one key per channel. So me and Austin, I need one key. Me and Matt, a different key. Me and Melissa, a different key, so on and so forth. Okay? This is Sam, isn't it?
Yeah.
You're on the front of our catalog.
Yeah.
With that redheaded girl. I saw you.
Oh,
Yeah,
yeah.
I saw that. I saw that. So.
It pays to be a leadership.
Yes. All right. But so one key per channel. Okay? So the number of users is n times n minus 1 divided by 2. Okay? So 4, there's 4 users. So it's 4 times 4 minus 1 divided by 2. So 4 times 3, which is 12 divided by 2 is 6. So if you look at the slide over here, you'll see we have the 4. We have A, B, C, D. See this? A, B, C, D. There's my 4 users. So there's 1 key, 2 key, 3 key, 4 key, 5 key, and 6 key. So for all 4 people to be able to talk with everybody else, we require 6 keys. Y'all see that? You will have to do this on a test. Multiple times. Everybody okay with that? Okay. We have authentication as long as the key is kept secret and you do not share. So if me and Austin here, if that key was shared with Matt, what happened?
Bad key.
Yeah, now Matt can read it and do whatever. Okay. Key distribution is a problem. Yeah, if you sit in the same room, not a big deal. But what if he's in Russia? Could be harder. But we know how to fix it. Okay, key management is always an issue. You have to store it, you have to safeguard it, you have to activate it, deactivate it. So, all right. So 8 users, how many keys? So 8 times 8 minus 1. So 8 times 7 is 56 divided by 2. 8 people, we need 28 keys. Easy enough. That's the math. It's pretty complicated, I know. You need to know that. Okay, asymmetric. Encryption key and decryption key are different. Now it's known as public key. We will cover this a whole bunch in depth, but you have 2 keys, a public and a private. Doesn't matter which one's which, as long as you don't mix them up. If I say this is my public key, it needs my public key forever. Can't be my public key today and swap it, and tomorrow it's my private key. That would be a problem. So there's 2 keys per user. So I need 2 keys, Austin needs 2 keys, Matt needs 2 keys, so on and so forth. Okay. So n times 2. 4 users, 8 keys, done. Everybody needs 2. Easy enough? So we have authentication as long as I keep my private key, as long as he keeps his private key, and he keeps his private key. Now what happens if Matt lets his private key out? Well, obviously both of his are bad. His public and private are both bad now. But does it affect my keys? No, it doesn't affect mine at all. Okay? Key management is easier, and again, we will cover this a whole bunch more in depth. The book Crypto talks about PGP with Phil Zimmerman. It's excellent. I tell you, you're going to ace the test if you read that book, because it does. It covers everything, but it's in story format. It's like reading Harry Potter or something, you know, but interesting. So, all right, a couple different types of ciphers. There's supposed to be a clock over there, and it's not. Is substitution ciphers. So replace each plaintext character with another character, just like you're doing for assignment 1. We can have transposition where we move things around. Okay, just different types of ciphers. Okay, we have a monoalphabetic cipher. This is the Caesar cipher, invented by Julius Caesar way back when they wore skirts. Okay, as a single alphabet, we shifted everything over by 3. So if we get the main alphabet, then we shifted everything over by 3. So A becomes D, B becomes E, C becomes F, D becomes G, so on and so forth. Okay? So we attack at dawn becomes Z, H, D, W, W, D, F, so on and so forth. Now you'll notice it's broken up into chunks of 5. Why would you think that would be? Makes it a little bit harder. Because didn't it, I mean, okay, a lot of you were young. Way back when I was young, you get the Sunday paper, and they had the daily jumble, whatever. You had to figure out, you always went for the one letter. Okay, if it's one letter, it's either I or, is that the only one single letter word? I or A. That's all you get. If it was 2 letters, it was it or an or you know, so you could solve it pretty quickly going by the length of the words. Now we don't know. Because if I gave you the cipher text, you're like, I don't know. But if I'd broken it up into, you know, 2, 2, and then 1, 2, 3, 4, 5, 6, so on and so forth, it would have been easier. All right. Shift 3 letters to the right. So return to Rome becomes that. Easy enough to do? That's your first assignment, by the way. It's pretty complicated. Okay, I will tell you, this is the first semester I'm ever going to do this. You need to know how to do this. I highly recommend you either write a program or find your website to do it. There's tons of free websites. I have no problem with you using them. Because everything I send you is going to be encrypted. Like emails and stuff. Sound good? Your test is going to be encrypted too. What? No, well, just Caesar Cipher. For now. Just Caesar Cipher. So you need, when you do your first assignment, you better know how to do it. Write a program to do it. Find a website to use it with. I mean, there's tons of them. If you type in Caesar Cipher Decoder, done, you find one. It's that easy. It's not hard to find. Okay? Because that's how I'm going to send you stuff. Because I got to thinking about it. If I use it that way, maybe you guys will figure it out. Because there's some people that are not going to get the first assignment correct. Even though it's rocket science like this, they're still going to get it wrong. Okay, I'm not pointing any fingers. No, just kidding. I'm not just kidding. But point is, just know how to do it. Okay? If you got questions, come and see me. I'm here all the time, it seems. All the damn time. Okay. So, monoalphabetic, again, is a single alphabet. It's also known as a monoalphabetic cipher. Now, we could also use it with a key. Now, here, rather than shifting by 3, we're actually using a key, which just happens to be 3. So, we're actually shifting with the word key. Okay? But we'll cover more about that when we get into more key-based ciphers. Okay? So, key-based cipher, we just shift it based on the length of a key. Substitution ciphers, we just substitute different letters. Could we substitute an A with an A? Sure we could. How about a C with a G? Sure we could. You just don't want to duplicate it. You don't want to substitute an A with an A and an A with a G. That would screw you up. Okay. So just different kinds of ciphers there. Breaking them. There's something called frequency distribution. Each letter has a characteristic distribution. English language is 0.0667. Okay? They make it trivial. Computers make this whole thing trivial. Anyone know what the most popular letter is in the English language? E. It's E. It is. Okay? So how can we, since we know E is the most popular, so if I had some text and I look at it and there's more E's than everything else, and if I figured out the frequency of E's and A's and all those, came out to 0.0667, we know it's English. Okay? What if we could get it so there is no most common letter? That was called frequency distribution. Okay? So right now, this is what we have in English. E is the most popular, so on and so forth. Okay? And we're going to get into how to calculate that, just not today. Okay, yes we are. But we're going to go into it more next time. Okay, the index sequence is a statistical measure of text that distinguishes text encrypted with a substitution cipher from plain text. Okay, this guy wrote a book, William Friedman, in 1922, been called the most important single publication in cryptography. Okay, here's how it works. It's defined by the probability that 2 randomly selected letters will be identical. So if I filled a hat with 26 letters, 1 of each letter in the English alphabet, so the odds of me pulling out an A is 1 out of 26. Do y'all agree with that? So what's the odds of pulling out a D? 1 out of 26. Easy enough, okay? Now, what if I had two hats? The probability of pulling out an A out of one and an A out of another is 1 over 26 times 1 over 26. It just is, trust me, okay? So the chance of drawing any pair would be 26 times 1 over 26 times 1 over 26, which ends up being 0.0385. That is the correct math, okay? I do cover this a little more next time as well. So, again, evenly distributed, for all 26 letters, but actually goes out to 0.0385, okay? English language is 0.0667 because the odds of pulling an E out is higher than pulling a Z out. See, this is for evenly distributed. So if this was true, when I said pulling an A out is 1 out of 26, but if this was correct, there should have been 13 E's for every A or whatever the math comes out to. Okay? Suppose we fill a hat with 100 letters, and the number of each represents the frequency. So there's 8 A's, 3 C's, 13 E's, so on and so forth. Okay? The chance of drawing a pair, so the chance of the A's, plus the chance of the B's, plus the chance of the C's, so on and so forth, it will end up being 0.0667. Okay? That's English. So then why are other languages different?
Words are spelled differently.
Right. Their language is different. Some of them don't even have the same number of letters. Some of them don't even have certain letters. Some of them have other letters. Go overseas and look at some keyboards. Try to find the @ symbol. It's like, what?
First time I went to Germany, I was going to use my wife's aunt's computer to send an email. I sat down and I don't have to look at the keyboard.
Right.
Okay, I heard everything. I just was talking to my wife, typing an email.
And you had all kinds of crap.
I looked down and was just like, what the hell?
Yeah.
And I look at the keyboards like, well, damn, I thought those were universal.
Yeah, they're not. They're very, very, very different. Okay? All right, so how is this useful? Index coincidence can be used to test. Now, this is a test question. It's test. It's going to be used to test if it's plain text or ciphertext. Okay? Text encrypted with a substitution cipher. Because remember, then we wouldn't know which letter. Remember, the substitution, we can do them any way we want. Okay? So it's about 0.385. English plain text would be 0.0667. Okay? We will cover this a little more later. Okay? So pretty much it allows computers to figure this stuff out pretty easily. Okay? All right, there are some references on it. I am planning on reading. I'm actually planning on reading this book here pretty quickly. David Kahn got a ton of books out there. But I think that's about it. We're about out of class time anyway. Yeah, we're going to start with Polyalphabetic next time. We're going to do more of index of coincidence. Okay? All right, that's the end of the second lecture.